So today we start refraction of light at a plane surface part 2 lecture. Okay. So now we start to discuss speed of light in different media, relationship between the refractive index and speed of light. Okay. So speed of light in different media, speed of light in different media and relation between and between refractive index and speed of light. Ri speed of light. Okay. So that's the important thing. The speed of light in vacuum is maximum. Speed of light in vacuum is max. Is 3 into 10 to the power 8 meter per second. That's the fixed value. Okay. But in terms of any other medium, vacuum is like more dense in medium, so speed of light is decreases. Okay. So refractive index is important. So speed of light in vacuum is maximum. Okay. So that refractive index of medium is generally defined the vacuum and absolute refractive index. Okay. So here vacuum maximum and any other medium. Okay. So medium is decreases. Like so mu refractive index defined as speed of light in vacuum. Speed of light in vacuum by speed of light in a medium, in a specific medium. Okay. And you know that speed of light is vacuum is always maximum. Specific medium is a little bit less than the maximum value. Okay. So here we check that any transparent medium. So any transparent medium. So conclude that any transparent medium. Okay. Any transparent medium. So mu is always greater than 1. Okay. Always greater than 1. Any transparent medium. Because that is the always speed of light in vacuum is much less than speed of light in vacuum is greater than greater speed of light in any medium, any specific medium. So that's why numerator is greater than denominator. So that fraction is always greater than 1 in transparent medium. Okay. So that is a definition of refractive index in terms of speed of light. Okay. So medium is obviously defined with respect to the vacuum. So speed of light is vacuum is always fixed, that is 3 into 10 to the power 8 meter per second by in any medium. Okay. Suppose conclude that speed of light in glass. If mu calculate what when light travel vacuum to glass. Vacuum to glass. So mu, let's check that mu is a start that is a n medium. Okay, to from, to from. So to from vacuum to glass medium. So like that, from vacuum to glass, or suppose mu is air. Vacuum means the speed of light is almost same, that okay, same as the vacuum. Okay, so or air, almost same. Okay, so air to glass. Okay, so start here and here. So that is equal to speed of light in vacuum is 3 into 10 to the power 8 meter per second, and vacuum 2 into 10 to for glass 3 into 10 to the power 8 meter per second. So cancel this, that is 3 by 2, that is equal to 1.5. That means speed of light uh, is decreases from air to glass. So rarer medium to denser medium, that is 1.5. Okay. So refractive index of glass. So Ri of glass, that is equal to mu air to glass, that is equal to 1.5. So Ri of glass is 1.5. Okay. So clear. So if that is obviously the refractive index is greater than 1, because the vacuum or air is maximum speed of light. Otherwise, the more dense light travel, so speed is it decreases. Okay, like another example, take a water. So similar consideration, from start to end, air light travels from air to water, that is equal to here we know that 3 into 10 to the power 8 meter per second, and you know that the mu is the unitless. Okay, because there is a difference ratio of same unit. Okay, so and water speed of light in water, that is 2.25, 2.25. Okay, so 2.25 into 10 to the power 8 meter per second. So if I cancel these two and these two, and we after solution 4, suppose consideration of 4 part 3, that is equal to 1.33. So Ri of water is, so similarly the Ri of water, refractive index of water, that is equal to mu starting to ending, from starting to end, from air or vacuum to water, air to water, that is equal to 1.33. That is air by water. Sorry, air, speed of light in air, speed of light in air by speed of light in water. Okay, that is the relation between speed and refractive index. Okay, so stress base concept is that the maximum the speed of light always in vacuum or air, almost nearly equal. Air and vacuum, that is almost nearly equal, 3 to 10 to 8 meter per second. But any other than the more denser medium, the speed of light is decreases. Okay. Suppose now the math general formula. What is general formula? If mu 1 to 2, from 1 to 2, that is means speed of light of speed of light in medium 1 by speed of light in medium 2. So you know that that is equal to, that is that's an important formula. Okay. So, the mathematical relation is mu 1 to 2 means velocity of light in one medium by velocity of light in medium 2. Now we divide C by, both side divide by C. Okay. Sorry, multi. Okay, C by V1. Okay. Uh, that is, sorry. No. Relation side. Now, if V1, so now that is some method is that is equal to 1 by V2. Okay, 1 by V2. So, if I multiply the C in numerator and denominator, V1 by C denominator into C by V2, both are same. So, here we see that. Okay, so if that is a multiplication, if that goes to denominator, that portion goes to denominator. Okay, so if that portion goes to denominator means C by V2 divided by C by V1. Okay, if I multiply this part, that is V1 by C. Okay, that part is replaced by these terms. Okay, that is replaced by this. Okay, and C by V2, we know that C by V2 from here, C, the basic RI formula, speed of light in vacuum by speed of light in any specific medium. So here speed of light in vacuum is C, so that is by specific medium. So refractive index of specific medium, so mu 2, what is mu 2? That is equal to speed of light in air by medium 2, that is refractive index of medium 2, that is Ri of medium 2. Similarly, mu 1, that is equal to air, from air to one medium, that is Ri of medium 1. Okay, so that is equal to C by V2, that is C. What is C? C is the speed of light. Okay, C is the speed of light. That is okay. That C, define the speed of light. C is the 3 into 10 to the power 8 meter per second. That is speed of light. So C by V1. So mu 2 by mu 1. Okay. So that is equal to mu 1 to 2. The boxes. That is important formula. So mu 1 to 2, that is equal to mu 2 to 1, means refractive index of medium 2 by refractive index of medium 1. That's the relation between refractive index of ratio of the two medium. Absolute refractive index. Okay. So why these are absolute? Because there is a speed of light, a reference. Okay. That C, the speed of light in vacuum or air, that is a reference. Okay. That's why the reference of vacuum, these are called absolute refractive index. So that's why these mu is called absolute refractive index. Okay. Now, very important, there is a take some examples. Okay. So these cases, the absolute refractive index here, that is C, that means the absolute refractive index. Now the important, there is some example. let's take an example here. Okay, example. So in mu, consider from water to glass. Light travels from water to glass. So that is means that velocity of light in water, velocity or speed of light, uh, light or speed in water, same in glass. And you know that the speed of light of water is 2.25 into 10 to the power 8 meter per second, by glass is 2 into 10 to the power 8 meter per second. Uh, both are same unit, so unit are cancel, these are also cancel. So if I solve these two, we get a 9 or 8 and get 1.125. Just simply divide. Okay, that means that 2.25. If I solve this point, this that is 0. Cancel by 25. 25 8 the 200 9 and 9 by 8. Okay, I divide this, so get a decimal number 1.125. That is the refractive index. Okay, when glass with respect to water, that means refractive index of, here is the important, that is Ri of glass with respect to water. Okay, that is 1.125. Okay, the Ri of glass, that is important. Now, what is absolute refractive index of glass? That is Ri of glass, or called absolute. So if I calculate absolute Ri, so that is equal to mu air to glass. We know that speed of light in air is 3 into 10 to the power 8 meter per second, and glass is 2 into 10 to the power 8 meter per second. So that's to cancel. That is 1.5. Okay, that is absolute refractive index of glass. So when you name added absolute, so absolute means light travels from air to glass, air with respect to air. So Ri of a glass with respect to, so that is important point, with respect to air or vacuum. Okay, that's mean absolute refractive index. Okay, clear? So always terms in here is absolute introduced here in Ri. So that means the light travels from air to some medium, any medium. Okay, from air. Okay, that's mean absolute refractive index. Next concept is discuss condition for ray of light. Condition for light ray passes undeviated in refraction. Very important condition. The condition for undeviated on refraction. Deviated on refraction. So first condition we discussed in previous lecture. If there is a consider two medium here, okay, one is rarer medium, another is a denser medium. There is a two medium. If that is the difference is these two medium is a density. If both medium have same density, okay. If okay, density is same. If I consider density is same, so there is no difference between these two medium. So that is both medium are same medium. That's why light travel from only a one medium. There is no boundary here. Okay. If there is no boundary here, so there is no deviated here. So that is a delta deviated angle is 0. The first condition is okay. So if both are same medium, okay, first condition is that if same medium, density of two medium are same. Density of two medium are same. And when the density of two medium are same, because both have the same materials, okay, the same medium, that's why both density of the same. And another condition is important, when I incident angle or reflected angle is 0 degree. In this case, here is the line of incidence, light fall perpendicular to the line of incidence or parallel to the normal, that is the incident ray, and here we draw a normal at that point of incidence, we get normal. Okay, yellow color represent normal. So this normal and incident ray are overlapping or they are parallel to each other. So that's why I equal to 0. And after striking the reflected ray same, okay, so also R equal to 0, because normal and incident ray and reflected ray both are parallel. Okay, so that's why like it absorb that this medium, so they also travel a parallel to normal. So that's why this condition which tells that the bound, so there is no deviation here. There is no deviation. So there is no deviation. No delta equal to 0. Okay. Number point 3. Okay. Now, if clear, if density of two medium are the same, if density of two mediums, that is a medium 1 and medium 2 are same, so refractive index of medium 1 and also equal to refractive index of medium 2. If both are refractive index are the same, okay. If both refractive index are same, so that's mean, so there is a no deviation here also. So that means delta becomes 0. So no deviation. If both medium refractive index of both medium are same. Okay. Now next topic. The relation between wavelength in the two medium. Relation between wavelength in the two medium. Okay. Suppose we consider the ray of light have same frequencies. Okay, when one color of light is suppose a red light. Okay, so both incident ray consider only one light. Incident ray one color light. Suppose a red. So that's why the frequency incident ray and refracted ray both are in red color, so frequency are the same, frequency same, f say. So frequency same, suppose consider that ray of light, consider that is a medium here, suppose that is a air medium. Okay, so on a air medium, that is equal to first medium one or air, that is considered upper part. Medium, there's a boundary line has a air, that is F, that is equal to C by lambda wavelength. And due to the suffer of refraction, so okay, here there is a refraction here, okay, so ray of light falls on that path, the incident ray, that is a normal. Okay, so as any medium, so there is a refraction. So obviously that is a denser than, so that's why bend towards normal. So that is a bending. If that is a incident ray, that is a, here is a bending. Okay, so here the frequency are the same, velocity v. Okay, and that is a change in wavelength lambda dash. So light at frequency A, wavelength lambda, suffer the refraction from air. The speed of light is c, and the medium which is speed of light is v. The frequency of light remain unchanged, equal to a. Okay, but the wavelength changes. So after refraction, the wavelength changes. Okay, the main changes are wavelength. Okay, so here that is equal to, compare these two. So c by lambda also equal to v by lambda dash, that is velocity we change. So there is a lambda dash, the new wavelength, that is equal to v by c times lambda. And what is v by c? That is, from here we discuss v by c. V by c, that is the mu. That is the speed of light in vacuum is c, any medium is v. So c by v is equal to mu, and here v by c, that means lambda dash equal to 1 upon mu times lambda, because c by v equal to mu, that is v by c equal to 1 by mu, that is lambda. Okay, so that's the important block here. The lambda dash new wavelength, that is equal to old wavelength by mu. Here the important factor is, if mu are relation between lambda here. Okay, so suppose here we check that there are two conditions here. If velocity increases, so mu is decreases, because velocity is inversely proportional to mu. And if velocity decreases, so mu is increases. Okay, so here we check that if similar condition here, if mu is increases, so lambda dash new wavelength is decreases. Okay, if mu is decreases and the lambda dash new wavelength also increases, so they are inversely proportional. So here the conclusion is that, when light passes from rarer to denser medium, so the main important conclusion is that when light passes from rarer to denser medium, light passes from rarer to denser medium. So here similar condition here, air to any medium, rarer to denser medium. So light passes from rarer to denser medium, so means the velocity, obviously here the velocity is decreases. If velocity is decreases, so mu is also increases. Because rarer to denser medium, if more density, so velocity decreases. So here we see that the velocity is decreases. In that case, velocity is decreases, so mu also increases. So that is a mu increases means mu greater than 1. If mu is greater than 1, if mu increases, so similarly if mu is increases here, now check that box. There is a one box, that is a C. Okay. One box. If mu is increases, so lambda is decreases. So rarer to denser. Okay. If here see that if denominator is greater than 1, okay, if denominator, check that as a parameter, is greater than 1, so obviously the lambda dash, okay, this is less than the lambda, because the lambda dash is decreases. If mu increases, the lambda dash is decreases, so that's why that factor also. So here the wavelength decreases. So new wavelength obviously less than that old wavelength. And another conclusion here is light passes from denser to rarer medium. So denser to rarer medium, same, denser to rarer medium. So that means some condition is denser to rarer medium. So light is back. Okay, similar path is maybe back is where that is a denser medium, that is a rarer medium. So we know that if that is a mu is less than 1, obviously. So here mu is less than 1, because take an example. Let's say now that that is a part A and that is a part B. So that is a part in suppose that is a numerator and that is a denominator. So fraction is 1 by something. So 1 by something, that is a less than 1. So actually here this condition, so V by C, actually this condition, light travel from denser medium to rarer medium, so C obviously more than V, so that's why that denominator is more than numerator, so fraction is obviously less than 1. So if mu is less, if here mu is small, see that box, mu is small, so lambda is increases, new wavelength. So wavelength, now this condition wavelength is increases. So lambda dash is greater than lambda, this condition. Clear? Okay. So today end the class here. Okay. If any doubt in that, so put in comment section. Thank you.